In this video, we'll look at some examples of absolute and conditional convergence. So the definition of absolute convergence is that a series with terms a sub n converges absolutely if the series with terms absolute value of a sub n converges. Then we have a theorem that says that a series that converges absolutely is convergent. Now that makes sense given the terminology. It would be kind of bad terminology if a series that converges absolutely didn't actually converge. But it is something that requires an argument to show that the fact that a series is absolutely convergent does mean that it's convergent. So most basic sort of example that we usually see in something like this is if we look at the series that goes from n equals 1 to infinity of, let's say, negative 1 to the n divided by n squared. So if we look at the absolute value of these terms, so negative 1 to the n divided by n squared inside of absolute values, what does that do? Well, n is always positive here, and the negative 1 to the n just becomes a 1 to the n, so this is the sum from n equals 1 to infinity of 1 over n squared, and this is a convergent p-series with p equal 2. And so what that says is the sum from n equals 1 to infinity of negative 1 to the n over n squared converges absolutely. And in fact, it converges as well. Okay, so what happens if we have something a little different? What happens if we have a series that converges, but if we look at the series formed by taking the absolute values of each term, we get something that's divergent? So this is what's known as conditional convergence. A series with terms a sub n converges conditionally if that series itself converges, but the series with terms absolute value of a sub n diverges. So the most common example of that is the sum from n equals 1 to infinity of negative 1 to the n over n. We don't actually know necessarily that this series converges yet. We can do this via the alternating series test, which is something that comes up in this section, but this actually is a convergent series. But if we look at the sum from n equals 1 to infinity of the absolute value of negative 1 to the n over n, this gets us the sum from n equals 1 to infinity of 1 over n, which is the harmonic series. So a p-series with p equal 1, and this thing diverges. Okay, so if we're willing to accept that the alternating harmonic here, the sum from n equals 1 to infinity of negative 1 to the n over n, if we're willing to accept that that converges, we can show that the series with absolute values diverges. So that means that the sum from n equals 1 to infinity, negative 1 to the n divided by n, is conditionally convergent. And I'll just note here that we know that this guy converges by the alternating series test, which we'll talk about in just a second. Okay, let's talk about the alternating series test. So an alternating series is one that alternates between being positive and negative with each term. It's not that it's sometimes positive and sometimes negative. It really has to alternate with each term. So suppose we have an eventually positive decreasing sequence with the limit as n goes to infinity of the terms of that sequence being 0, then the statement of the alternating series test is that the series negative 1 to the n minus 1 times b sub n converges. Okay? So the terms have to go to 0, and the absolute value of the terms has to be decreasing. So let's look at an example of this. Let's look at the sum from n equals, let's go from 2 to infinity, of negative 1 to the n minus 1 log n over n. I'm starting at 2 just to avoid the numerator being 0 on the first term here. There's no reason that I really need to do that because the alternating series test just talks about the sequence being eventually positive, but let's just do it for just to be completely clear here. Okay, so what is this here? Well, if we're trying to figure out what the statement of the theorems says, this here is our b sub n. Okay, those are our b sub n's. And if I look at log n divided by n, and I look at the sequence formed by these terms, this is always positive for n greater than or equal to 2. So log 1 is 0, and log 2 and everything after that is always positive. Of course, n is always positive for n greater than or equal to 2. So we have a positive sequence here. So we have a couple things to check here. So first thing to check is log n divided by n a decreasing sequence? Well, there are various ways you could argue that. Let's just try to be absolutely clear here. So let's look at the derivative of log x over x. If we can show the derivative of log x over x is negative, then we'll be able to show that that's a decreasing function, and therefore we have a decreasing sequence in log n divided by n. Okay, so what is this? This is, if I take the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. If we simplify this, this is 1 minus log x divided by x squared. Okay, so what does this say here? Well, if I look at each component of this, this thing is going to be positive for x greater than or equal to 2. This thing on top, well, if 1 is equal to log x, that says that x is equal to e if I exponentiate both sides, which is roughly 2.7. So what this tells us is that this thing here is going to be negative for x greater than e. Okay? So what this tells us is that log n divided by n is eventually decreasing. Okay, the derivative is eventually negative, and so the sequence is eventually decreasing. What else do we have to check? Well, we have to check is the limit as n goes to infinity of log n divided by n equal to 0. Well, if we look at log n goes to infinity as n goes to infinity, and n goes to infinity, obviously, as n goes to infinity. So we have an indeterminate form here. Now, again, this is something that we've sort of looked at before in calculus, but let's just do it carefully. So if I look at the limit as x goes to infinity of log x over x, so that I have something continuous here, and I can use L'Hopital's rule. This is, by L'Hopital's rule, the limit as x goes to infinity of 1 over x divided by 1, which as x goes to infinity is 0 over 1, which is 0. And so that tells us that the limit as n goes to infinity of log n over n is equal to 0, like we wanted. Okay, so we've fulfilled both conditions of the alternating series test, and so we can say that by the alternating series test, the series converges. One of the nice things about alternating series is that they're actually very easy to estimate. So let's suppose we have a series, an alternating series that converges by the alternating series test. And what this result says is that the actual sum of the series minus the nth partial sum, so if you look at the difference between those two things, which is how we often like to estimate series, that the error there is less than the magnitude of the capital N plus first term. So we just need to look at the next term, and therefore we can compute very easily what that error is going to be. So, for example, if we have the sum from n equals 1 to infinity of negative 1 to the n minus 1 times 1 over n squared, and we know this converges via the alternating series test, and I won't actually do that there. Let's ask how many terms should we sum to get within, let's say, 0.01 of the actual sum. Okay, well, our error in absolute value is less than bn plus 1, so the capital N plus first term, which is equal to 1 over capital N plus 1 squared. Okay, so we want this amount to be less than 0.01. Okay, well, so this means if I flip both sides, this is capital N plus 1 squared should be greater than 100, taking the reciprocal of each side. And so this means that, so obviously 10 squared is equal to 100, and so what I have here is that n should be greater than 9. Okay, 9 plus 1 is 10, 10 squared is 100, so n should actually be greater than 9 in order to make that inequality true, and thus we need at least, let's say, 10 terms, since n should be greater than 9, so we'll pick at least 10 terms in order to ensure our error is less than 0.01. Okay, let's look at one more example here, and this is going to be a case in which we don't have an alternating series, we have something sort of different. So we have the sum from n equals 1 to infinity of cosine n over n squared. So certainly the terms of this series are sometimes positive and sometimes negative, but it's not in a regular sort of way. It's not like we have a positive, then a negative, and a negative, etc. And so it's not entirely clear what method to use here, and this is one of these cases that in which absolute convergence can really tell us something kind of helpful. So what do we think this does, first of all? We might think, so we might guess that this series is similar to the p-series, n equals 1 to infinity of 1 over n squared, right? A p-series that converges. Okay, so we think that it has that sort of behavior, but we don't really have a test for this because these terms are not alternating and they're not always positive. So one trick here is, let's look at this series instead. So let's look at the sum from n equals 1 to infinity, the absolute value of cosine n over n squared. Okay, so this has all non-negative terms. And because we have two series now with non-negative terms, we can use something like the direct comparison test. So we know that the absolute value of cosine n is less than or equal to 1, right? Because that's negative 1 is less than or equal to cosine of anything is less than or equal to 1. And so we know that the absolute value of cosine n over n squared is less than or equal to 1 over n squared. Okay? So by the direct comparison test, since this p-series, n equals 1 to infinity of 1 over n squared, converges, so does the series from n equals 1 to infinity of the absolute value of cosine n over n squared. Okay? But that's not the series we started with. So what that does say is the series that we started with, the sum from n equals 1 to infinity of cosine n over n squared, it does tell us that this converges absolutely. Okay, so it's absolutely convergent. So we've actually proven something a little bit stronger than what we started with. And instead of answering whether this converges or diverges, we actually showed that the series converges absolutely, and therefore the sum from n equals 1 to infinity of cosine n over n squared actually converges. So this is a nice way of looking at a different series, showing something that's a little bit stronger, showing that series converges, that the series we started with converges absolutely, which is enough to tell us that the series itself converges.